Okay, it's my great pleasure to introduce Josef, Svoboda. So here we'll talk about GPPV invariants and the spectrum.
Okay, so my talk is about the relation of some invariants, which you already know from the books or lectures, and some invariants which come from geometry. So basically, it is about the interplay of low-dimensional topology and low-dimensional geometry, which is a very vast and broad subject. So our goal is, in general, to study analytic singularities, so singularities of some holomorphic or algebraic functions via topology and vice versa. So we can also maybe say something about the topology of three manifolds using the analytic singularities. So here is the typical picture. So if you take a singularity given by x squared equals y cubed, so it's a cusp. So this lives inside C2, so it's not easy to draw. But if you intersect with a free sphere around this singular point, which lies in the center of C2, then you will get a node inside this C3 on the. So it kind of tells you that the singularity gives you some non-trivial topology. So the node which you will get is E23, the torus node or trefoil node. In general, you could get other chloride nodes or some cables of them. You cannot get hyperbolic nodes by this. Just those kind of simple nodes. But there are still questions which are not easy, even about those simple nodes. So I will start with saying some basic definitions and properties of hypersurface singularities. So I consider as my data a polynomial f of some variables x, y, z in n variables, and it should satisfy that all the partial derivatives are zero exactly at the origin and nowhere else close to it. So then we say that f defines an isolated hypersurface singularity, because this f, the zero set of f is a surface, right, or in general hypersurface, and this condition on the partial derivatives tells us that actually there is a singular point on this hypersurface at zero, and it's isolated. There are no other singular points near to it. So then we can study it by considering near fiber. So we take a slightly different equation. F equals some small number t, and we also intersect it with a ball around the origin with small epsilon radius. So this is called modular fiber, and it's a smooth. So I will say just for surfaces, then you think what are the dimensions. So if you have a surface with three variables, then it will be a smooth four manifold. And it's an open four manifold. It has a boundary, and so here in this picture we have this preimage of zero in the function f. So this is our singular surface and zero, and then we take some closed value t, and we have a preimage which is this empty, the modular fiber. And moreover, it is not just a smooth manifold, but we can consider it in all nearby points, and it gives us, by a theorem of Milnor, a smooth local trivial vibration of open four manifolds. So this is very nice because it gives us a monodromic transformation. So we can go around the loop, around the zero. And because of this local trivial vibration, we can always find a diffeomorphism between two fibers. And if we go around, we will get the so-called monodromy, and we only consider its action on homology, so on some vector space assigned to this modular fiber. Yeah, so this is monodromy, and this is one way how to get some invariance of this singularity, because for example we can consider eigenvalues of this monodromy, which are numbers. Yeah. And one more thing I want to define is this ring of the singularity. So this is exactly the boundary of the modular fiber. So for surfaces, it is just a three manifold. And one important thing is that it's actually also a boundary of this singular surface if you intersect it with the three sphere. So this is a property of isolated singularities, that you can find the same manifolds, homologic manifolds here and also here. So the basic question is how much of the analytic properties of the singularity we can get out of this three manifold. Okay, so this is the link of singularity. It's a little confusing because links are also like a bunch of nodes, so this is a different meaning of the same word. Yeah, so this is a three manifold. If you take a curved singularity, you will get an honest link because or not. Yeah, so yeah, so now we want to talk about these invariants of hypersurface singularities. So one way how to construct them is by resolving the singularities, so finding a non-single surface which with a map which is it's like isomorphisms everywhere except this over this singular point, or by this smoothing, so finding this near this smooth fiber. So this is what we were doing in the previous slide. So this is this modular fiber and modular. So some numerical invariants, there are many invariants. So the most important are probably the modular number. So this is the dimension of this homology. It's actually just the middle homology because the other are vanishing. Then signature. So this is a form manifold. So it has some intersection form, and you can take the signature of this intersection form. Or geometric genus, which we can define by this resolution. So we take the resolution and we take page one of the structure sheet. So this is one way how to define the geometric genus. Okay, and then we have some more refined invariants. So we can take, for example, this eigenvalues of the monodromy. And there is a fancy invariant which is called spectrum, and this talk is called spectrum. I will not present the definition, but basically eigenvalues of the monodromy are some roots of unity, again bounded by some theorem of Milnor, I guess. So you can ask if there are some natural logarithms, like if you have e to the 2 pi I by 4. Can you take like you can take different logarithms, right? But they differ by integers. So if you add some information which is very deep and it's only theoretical, so on the modular fiber, there is actually a mixed wedge structure which tells you which logarithms you should take. So I will present it on an example. So if you take, oh sorry, there is a mistake. There should be 5 here. So if you take E8 singularity, which is x squared plus y cubed plus e fifth, then modular number is 8, which is also here, right? So this means that there are kind of like there is 8-dimensional lattice of the middle dimensional homology. Signature is also 8, yeah, because this is a positive definite lattice, and the geometric genus is just 0. And in fact, those are kind of related. We have to always come to the third one. So, and here is the spectrum. So, if you want to first know how the eigenvalues of the monodromy apply, just take these 6. I hope you can see that there are 8 numbers between in the interval -1 to 2. So, if you would take e to the 2 pi I and these rational numbers, you would get the eigenvalues of the monodromy. But the spectrum tells you that there are actually some natural logarithms which live exactly in this interval. So it could be, so this is like 1/30. It could be also you know, 1/30 minus 1, but it's not. So the Hodge theory tells you that all the natural logarithms live in this interval 0, 1. But in general, for a surface, they can be spread on this interval -1. So yeah, and the spectrum. So one reason why it is really great is that it satisfies very strong properties. One of them, probably the most important, is the semi-continuity property. So if you can take this singularity, the polynomial, you can deform it to some other one, for example, to P7, which is given by this equation. And if you look at the spectrum now, it has 7 points because the number of the elements of the spectrum is this modular number. So it's basically a refinement of this modular number. And the semi-continuity property says that if you take any interval of length 1, then there will be less points here than here. So it is not just that there are less of them, but there are kind of, in any interval, there are less of them, or equal.
So you said the spectrum is a spectrum of a certain operator, but
So
you define that operator?
Yeah, so this is yeah, so this is basically the spectrum of an operator.
So what is the operator? I don't see
Yeah,
it.
so here there is no operator. This is you can think about like you can take like a logarithm of this d, but there is this it's not really a spectrum of an operator. This is just a name. I mean,
Yeah, but what's the definition?
yeah, I didn't say the definition, but that's what I want to avoid. But basically, you ask which what logarithm you want to take for an equality of a monotropic.
No. But I understand. The
Yes.
model here, I still don't know. Maybe you say later what is the spectrum exactly?
Yeah, I'm not gonna say it. It's a bunch of rational numbers in the interval -1 to 2. And you have a so monodrome is clear, I hope. In the Hodge theory, you have the homology. So the monodrome acts on the homology, and there is this filtration, Hodge filtration.
Yeah.
So Hodge filtration tells you if which of these 3 intervals you choose.
Or because there are 3 weights that
Yes.
contribute.
So so you split like homology on these eigenspaces, and then you split it even more by the filtration. And so this will tell you the intervals. Is it okay?
Yeah.
Okay. So this is the spectrum. So now I want to talk about the difference between curve case and singular and surface case because it's quite different. So curve singularity, for example, this E2 singularity, which gives us trigonal. So the link is an honest link, or in this case, actually not, because there's just one branch of the singularity. And what matters is really this embedding in S3, right? Because otherwise, not is just a bunch of circles. So this is really important that we still think about it embedded in S3. And we can define, of course, we can define Alexander polynomial of this knot, and it's actually the characteristic polynomial of this monodrome transformation. So this is basically the same information. This like eigenvalues of monodromy or roots of Alexander polynomial, and we can go further. So this is work of Schende and Mauri, and then the conjecture and then proved by Oblomkov, which says that you can also express the homology polynomial, which is a generalization of Alexander polynomial, using some Euler characteristics of some pieces of the Hilbert scheme for this. So using some analytical information. So this is like a very interesting story, but so far there is no analogy in the higher dimensions. So, but there are many hopes, but so far, yeah. So in the surface case, the link is suddenly like a non-trivial 3 manifold. Yeah, so it's usually not as S3. When it's S3, it's actually just the A1 singularity. It's nebulous. So now the topology of this 3 manifold matters, and not so much the embedding into S5, or maybe the embedding into S5 matters, but nobody really knows how to work with. Yeah. The problem is that you can you can try to define Alexander polynomial, but this only works for S3 embedded into S5. And there are some problems when you want to define it for, so you can define it. You can take like a cipher surface, which will be for manifold, but then it depends on the choice. So there are some papers on this, but it's so far it's not really very clear. So that's why we kind of forget about the embedding and we only care about the topology of this three manifold, which still gives us some information about the singularity. Yeah, and so for example, we can ask what is the meaning of geometric genus, and there is a nice work of Nemeti and his collaborators which relate to this hybrid with an invariance of this three manifold. So yeah, and so there is this question how to define the Alexander polynomials. Yeah.
Are there examples? I presume there are examples known where you have two surface singularities that have the same homeomorphic three manifolds.
Yes.
With different embeddings.
Yeah. So yeah, you can have many like so of course you have many singularities which have different morphic labels. So yeah, you're losing a lot of information. That's true, and you would like to use this embedding, but there. Yeah, the problem is how. Yeah. So you're definitely losing a lot of information, and the question is how much is still there. And this is a really interesting subject. So I will give you an example. So the example will be a Poincare sphere. You probably know, but one way how to do it, like to geometrically, is to take this dodecahedron and glue its solid dodecahedron, and you glue the opposite sides by this rotation by 1 meter, like 1/5 of the full length. So this is the Poincare sphere, but we will not think about it in this way. We will think about it as a link of this singularity x squared plus y cubed plus c5. Sorry, there should be c here. Another mistake. So what are the properties of such a link? So it's a three manifold. It's closed. It's full. And it's almost like a sphere, right? Because if you compute the homology, you will find that it's the same as the homology of free sphere. So this is what we call this homology sphere. If it is true only up to rational numbers, then we call it Q homology sphere, rational homology sphere. But still, it's not a free sphere because if you compute the first one in the group, then it has 120 elements. So, and another property is that we have this boundary. It's a boundary of this Milnor hyper, and as I said, this is a four manifold with intersection form E8. Okay. So yeah. So this is just a preparation, and now I will come to the main point. This is about so there has been this work of Lorentz and Zagier on some more involved three manifold invariants and how they could potentially produce modular forms, so some number theoretic. So this is just so we want to explore now the modularity properties of three manifold invariants. So which invariants we take? So we start with the three sphere, the Poincare sphere. And we want to study Chern-Simons theory, so Chern-Simons invariant of connections. And there is this more refined story of Wittmann-Reshetnik-Turev, Chern-Simons theory, or this GPPV invariance Z-head, which Hugo was talking about in his lectures. So those are invariants which produce modular forms, and there are of course related to this Chern-Simons. So now I will talk about this in the Lorentz-Zagier paper from 1999. So they consider two functions which are written as some Q series, and so there is the first clue is that the Chern-Simons is kind of clear, the values of the Chern-Simons for two non-negative connections. And what they prove is that the Wittmann-Reshetnik-Turev invariants are limits when you take this first function and you go to the root of unity. So those are homomorphic functions on unities. And if you go to a root of unity, so we also saw this in Google's lecture, right? That we can approach roots of unity and we recover some. We recover this invariance. So you can ask what is the role of this second function, because there is no relation to Brieskorn, or at least there is no obvious relation. And this second function serves kind of as a friend of this first function. So that together they have a nice modular property. So together they transform as a modular form of vector valued modular form. So this is the Lorentz here. Yeah, I was a little bit too precise. So you have to first take this Eichler integral of this theta function. So you kind of remove some of the modular properties, and you get this false theta function. And then when you take the radial limits to the roots of unity, you recover WRT. Yeah, so now here comes an observation of possible relation with the spectrum. So if you look at the spectrum of A, there are 8 numbers. You see them here on between 0 and 1. And so if you look at this coefficient, so you have this like 1, 11, 19, 29 here, here, and you have this 7, 13, 17, 23 here. So of course it can be just a coincidence, you know. So this was kind of the beginning of our investigation. That I saw these numbers in the paper, and I knew what is the spectrum. Also, this number 30 is kind of here because when you generalize these formulas, you always have 4 times some number here. So this kind of gives us a question if this can be generalized. So if we can, and what is the meaning of this relation? Yeah. So can we say something about the spectrum from the architecture or the other way? The big goal would be maybe so the spectrum has some, so it has these deep properties, semi-continuity, and it can be also defined using the stability conditions on a direct category. So like a future goal would be to use some of these relations to kind of define a WRT for a category, but so far we don't know how to approach this.
That's a good question. So you're going back to this Hodge theory in the wave equation.
Yes,
so
yes.
The colors here match the equation.
Colors?
The colors you have blue and red.
No, because for this T8 example, the Hodge theory is kind of dumb because there is nothing in this interval and there is nothing in this interval. So everything is just in 0, 1, yeah, which is special property of ADE singularities. So the simple. So these colors, this like how you like your question is basically like which one should be which. Why are some red and why are some blue? Yeah. So this is something to do with. Maybe I will show you next slide when. Okay.
Maybe before you move.
Yeah.
Okay. One more follow-up question. So how do you know that to pick the number 49?
Sorry.
When you define theta minus, why 49?
This one.
No. Q to the 49. Excellent. Theta minus is defined in terms of Q to the 49 over 110, right?
Yeah, here.
Yeah. Why do you pick 49 and not 70?
Yeah. I mean, you should ask Lorentz and Xavier. Yeah, because
is there an algorithm or
they
formula?
I mean, yeah, I will. Basically, the answer is yes, and those are the values of the church samples.
Oh, 1 and 49 are
so the 49 over 120 is the church samples of one of the collections. Value of the church samples. You have 2 non-abelian connections. So
no, always. Right.
Yeah. Okay. Yeah. But yeah. And I mean, there is a natural formula for these exponents, and you can kind of get out one of these, the one rational number, so that all the other exponents will be integers. Yeah, so I think it will be maybe. Okay. So these are the say natural. So these are the definitions I need. So this is the usual notation from modular forms. So you know you equal to pi I tau and y equal to pi I z. Actually, I don't use this here, so forget about it. So if I take the positive integer n and I take the residue class modulo 2n, then I can define this weight 3 to unary theta function as this infinite sum over all numbers in this residue class. And I take L times this q to this quadratic term L squared over 4n. So you see here that there is this 4 times 30 in compressed here. And this number is not an integer, but it's like an integer up to a common rational part, which you can take out, and this is this 49 over 120. And so this is the theta function, and theta functions, so what is nice about them, they form this rank 2m vector value modular form with weight 3/2. So you can take all of them as a vector, and if you plug here -1 over tau, they will transform very nicely. So you will find the matrices S and T, which give you some representation of SL2Z, the double cover of SL2Z. So these functions have together, if you take all the classes, all the residue classes, they have a nice modular property. And false theta function or this Untitled integral is basically the same thing, except that you kind of change the signs here. So there are some funny signs. And this means that the modularity property are not so nice, but it still satisfies some weaker modular property. These quantum modular forms of false theta functions. Yeah, so this is what is related to WRT. So this is this Untitled integral there. Yeah, and so now I can express these functions here. So I didn't write the coefficients there, but now I can express them as a linear combinations of these theta functions. And as I said, I consider two of them, so there should be minus here, sorry, because then I can find matrices T and S such that these functions transform according to these matrices, which is very nice. The spectrum of the once again. So yeah, so so the basic question is we can construct this function, which this is kind of what Foucault and his collaborators were doing, and also find this theta function or linear combination of theta functions which give you WRT as a radial limit, and then find some other functions such that together it's a modular form. So this is there are some examples in the paper of Chen, Foucault, and collaborators, but still, I think it's kind of like open. Yeah, we don't really know how to do it, how to find the modular forms. So I'll show you one more example. So this is Brieskorn sphere is a single, so it's a length of a singularity which is given by this nice diagonal form. And I also want these three numbers to be co-prime so that the length is a homology sphere. So the first example was x squared plus y cubed plus z5, which gives us one prime homology sphere. So this is kind of the easiest example, and also kind of weird in a sense. And then we have infinitely many other Brieskorn spheres if we take the other whole-prime triples of integers and we consider such as singularities. So okay, so now I'm just writing the false theta functions, which are in the paper of Chen, Foucault, and others. So in the previous thing we had 2 of them, and now we have 6 of them, and I'm writing the false theta functions directly. If you ask which one where you will recover this z hat or this WRT, so I should say that there is just one z hat here because it's a homology sphere. So this Foucault was talking about the thing that you label this by elements of H1, and H1 is trivial for homology spheres. That's the definition of a homology sphere. So there is just one z0, which is a pure series, and it recovers WRT. And it's in this fifth row. And you can somehow find 5 others such that together it transforms as a modular form. So they give some procedure. It was also done in an incoming paper, so there was a lot of work on this. So you may ask, what is the meaning of all these numbers, right? So how do you get them? So you can express them really explicitly. So my point is now that I want to change them slightly. So what I'm doing here, I'm basically so these theta functions or these they have kind of like periodicity properties. So if you take m and you take some k, then it's the same thing as if you would take m and 2m plus k. Yeah, so you can, so they're periodic by 2m. And also if you take m and minus k, then you have minus of psi of m. So you can kind of flip some of the signs using the or you can, for example, here you have like minus 50. You have 53 and sorry, here there is a 47 and I change it to 73. So I go here modulo 220. And so here all the numbers are in the interval 0 to 120. Actually even like 0 to 60. But there are these funny signs everywhere. So, so I change it such that the signs are now in the coefficients, and all the signs it's outside are plus. So this is the same thing, except that those are basis vectors of some SL2Z representation. So I multiply all of them by -1. So it should just change the basis. But now there are some numbers which kind of escape the interval 0 to 60, but the form is nicer because they are just summing positive. There is always a positive combination of theta functions. And now we can observe that these numbers, starting with -30 and ending with 73, if we divide them all by 60. We will get this spectrum of this singularity x3 plus y4 plus t5. So this relation is kind of preserved for all the Brieskorn spheres.
So now the Hodge theory becomes more interesting.
Yes, exactly. Now the Hodge theory becomes more interesting because we have something which is out of the interval. Yeah, and this is kind of what was kind of missing in this story, because people were trying to put everything into interval 0, 1, yeah. But it's natural to consider this like yeah.
Maybe another type of question, looking at both the previous example and this example. So these are refinements of the Katzarkov invariant.
Yeah. So that's a good question. So Katzarkov invariant is kind of counting the connections.
Right.
And Katzarkov invariant, now I didn't write it here, but so Katzarkov invariant is hyperwritten, and so Katzarkov is some sign count of the connections.
Yeah.
And it is for Brieskorn spheres is equal signature divided by A or something. So signature is basically a sign count of the elements of the spectrum. You take like the number of elements in this interval minus number of elements in this interval plus number of elements in this interval. So this is kind of a lift of this story. And then the next lift is to take like abelian non-abelian connections.
So in the first example, the Katzarkov invariant is 1, and here it's 1. For 2, 3, 5 is Katzarkov is 1, and for 3, 4, 5.
Yeah, I would need to
I'm just trying to understand it.
dots and divide by 8. That's right. I don't want to compute it now, but
So it's a strong invariant, right? Like
Yeah.
Distinguishes spheres with the same
Yeah.
in principle.
It's very easy to compute. from here. Actually, there is, so I told you this, so this is kind of length of this story with Katzarkov invariant. And it's very interesting to ask this question because this Katzarkov invariant it can be pushed to more general singularities when we go from Katzarkov to this hypersurface. And so far, this works only for like Brieskorn spheres and AT singularities. So this is kind of the next step. We would like to put it together with this hypersurface story. So if you look at the rows, so they label the SU2 or sorry SL2C irreducible connections, and some of them are complex, and some of them can be conjugated to SL2R. And the SL2R connections are exactly those which correspond to these numbers which don't have negative numbers. Okay, so yeah, and Katzarkov invariant is kind of a sign out here. So yeah, so this was a very nice question. So yeah, and the one important thing or interesting thing is that the Z0 actually corresponds to the smallest number in the spectrum. And you can, I mean, not just the smallest number, but there is this, you asked about this red and blue numbers. So there is a natural action of Z2 times Z2, just the four element group, which groups, like, which gives you these groups of numbers. And this is kind of what you have when you compute the Katzarkov invariant. You assign to each connection like these three integers. But then you model by some action, by Z2 times Z2 action. So this is exactly what is doing here, and this is the action. I didn't write it here, but basically it's just like some kind of this symmetry of the spectrum here. This spectrum is composed by here by three spectra of these three polynomials, and they all have this symmetry. So you can play with these symmetries, and you will recover this action. Okay, so the last thing I want to talk about is so this is the study for Brieskorn spheres, which is kind of clear, and then it took me a lot of time to realize how to proceed further. So the next example, and so far the only, are the AT singularities. So AT singularities are the simplest kinds of singularities. They are labeled by linking diagrams. And in terms of the spectrum, they can be like classified by spectrum. But so there are exactly those singularities whose spectrum is in the interval 0 to 1. So they're very special from this point of view. Yeah, and so if you want to generalize this correspondence of the spectrum and these false theta functions, so the false theta functions are here. So if we just try, we compute the spectrum of say V6, it will not work. But we can pass through the universal abelian cover of the singularity. So, for example, if you have E6, so now the link is not a homology sphere, but it's a Q homology sphere. So this means that there is some torsion in H1. And it's actually the torsion is just Z3, so three elements. And you can find a covering of this. So you take the germ of the singularity, and you can find a covering such that three sheet covering by the singularity D4. So it's easy to see. You have this like, sorry, there should be C again. So if you take like an action of third roots of unity on this Y and Z, then when you do the quotient, you will recover E6. So this is the universal abelian cover, and this is also being studied by Paul and Clementi and many other people, because even if you have kind of ugly singularity, usually the universal abelian cover is very nice. It's like the Brieskorn complete intersection. Yeah. And if you ask how you can like get this by very simple thing, so you can take this link of the singularity, and it has this cipher invariants. So the denominators are 2, 3, 3. So if you just consider x squared plus y cubed plus z cubed, you will get this abelian cover. So in a sense, it just depends on a topology of this link of So if you now look at the spectrum of D4, so it's 1, 6, 3, 6, there is this multiplicity here, which is another interesting phenomenon. And you will look at the so now there are in general more CVs, these invariants, and you can still ask if there is a modular form such that there are components of this modular form, at least some of them, and you will find this C61, C6 plus C65, and 2 times C60. There is some kind of a natural basis for this, such that you will have 2 here. So this kind of corresponds nicely to this spectrum of D4, and you can do it for all the AD singularities. For example, if you take just A singularities, then I don't have it on the side, but if you take A singularities, then the universal abelian cover is just C2, because this is a quotient singularity of C2. So there is no singularity for the universal abelian cover. It's just non-singular plane. So the spectrum is empty. And also, if you look at the Z heads, so they're non-zero. There is like a 0, 0, 1 up to n. Most of them are 0, but those are some q to some power, which I don't remember. But the point is that this is just a rational function in q, and there are no theta functions. So it's kind of silly. This example is kind of silly, but it again corresponds. There are no theta functions. This is like an empty thing. So yeah.
Can you go to the next slide? I have a quick question.
Yeah.
You said there is this multiplicity 3/6, 3/6. So that's the maximum multiplicity because these are surface singularities. So I know for the usual monodromy, the multiplicity is at most 2 here, right? By this term of never.
The multiplicities of elements of spectrum can be
Yeah.
very, very high.
No, but for the monodromy mean of federation, there is above, which is a dimension. Yeah, the eigenvalues of the monodromy. But for the spectrum, they can be bigger.
Yes, sir, I need to think about it, but I can talk about it. Yeah. So I just want to finish by some questions. So I actually like mentioned some of them already. So one thing is to generalize to other singularities. So next step would be this Arnold 14 exceptional singularities, because they are very similar to ADE. But the problem is that I don't really, it's not really clear to me this business with multiplicities. This is just like here it works nice, but there I still don't understand it, and the universal cover have high multiplicities. So I hope that it will work at least for some more general singularities. But in general, it might not work. We might have to take something more refined than just the universal abelian cover. So this is related to this work of MND and collaborators, as I mentioned, that you have these 3D cyber invariants, which are labeled by spin C structures or elements of H1. So you can recover Katzarkov invariant if you take some canonical spin C structure, which is given by the analytic structure of the singularity. But there has been a lot of work on the relation of these cyber invariants with the geometric genus or something more refined. And the geometric genus is basically counting of some elements of the spectrum. So for me, there is some hope that this could be kind of lifted to the spectrum and to this Z heads from so PG would be lifted to the spectrum, and this cyber meter would be lifted to these Z heads because they are labeled by the same thing now. Yeah, but I learned only recently about some of these papers. So, and yeah, the funny thing is that they also talk a lot about universal equivalent covers. Actually, there are some conjectures on universal equivalent covers, how nice they are, and this is somehow related to this how, because this you can find counter examples for like you can find ugly universal equivalent covers, and you can also find problems with this relation of cyber-equivalent and the geometric genius. And those counter examples, they seem to be related. So I think there is a lot of interesting things to think about here. Yeah, and so then of course the main goal is to find this modular form for other three manifolds. So as I said, there has been some work on this, but there are some like proposed formulas, but they seem to not work, or I mean at least in some examples. So this must be like we have to think about it, and maybe we can use these ideas to construct this modular form like naturally from the topology of the three manifold. So far it is done by kind of heuristic method that we compute these heads, and then we look for like a representation which might fit it, and then we look which one is going. This is the work of chain Foucault. So they found many examples which go beyond me, but yes, still there is not much understanding of this modular form, at least from what I know. Yeah. So then the last question is: so is there a conceptual explanation of this relation? So the funny thing is that Nemeti, in his speech in the International Congress of Mathematicians, he calls this relation of cyber-equivalent and geometric genius, he calls it conjecture/coincidence. So it seems that he's not even sure if there is a deeper meaning in this, even though you can do it for many examples. You can do it for all quasi-homogeneous singularities. Yeah, so this can be also some kind of funny coincidence, just like the variant of this. So yeah, so if there is a conceptual explanation, we could maybe try to use the semi-continuity or the topology, or we could use some of these. So this ZWRT or Z, those are some topological quantum field theories. So we could try to use it to study the analytic properties. So here are some references. Of course, there are so many. So I just mentioned. This is the work on the modularity. This is the invariants. This is heads, and in this incoming paper, he kind of gives these numbers. They are all known. This is just kind of a interpretation of them. And this is the original paper. So I think I'll stop here.
Any question? Relation.
Well, this so you
Can you use this translation or this figure for how much?
yeah. I didn't include the table, but so there are not so many singularities easily listed. So for example, in E7 singularities, you would have three functions here, and two of them corresponds to these Z heads, but one of them is kind of additional to make the whole thing a modular form. And the labels, I mean, they just numerically correspond to these elements of the spectrum. I don't know. I mean, you can, if you want to, so I mean, you can ask. Maybe it's fishy. And maybe there is no clear role of the spectrum. So these numbers, they are really easy. You just take like numbers from 0 to this exponent, 0 to this exponent, 0 to this exponent divided by the exponents, and then you sum them up with all possible ways. So you will get these numbers, And so what I'm saying is that these labels which occur in this modular form are just of this simple type. There is no magic there. Yeah, and somehow it's not clear if it's real. I mean, if there is really a deep relation to the spectrum, but it might be because we have this story of MLT, which relates some counting of elements of spectrum with counting of connections.
Is there any other symmetry?
Is there any mirror symmetry? I think this is a question for you, right? Or Katzarkov. This is like a part of the paper we are preparing with Katzarkov and Kyoung-Seog Lee. So
What I mean, this program which involve some group action on this singularity. So is there some
yeah.
kind of
I know what you are. Yeah. So there is this story of Takahashi and Evelyn, right? I try to relate it to this, but it's not really clear to me. Yeah, you can think about some equivariant spectrum, like this. So this is just a plain spectrum.
other question? If not, let's thank you.